Hi everyone, this is Yin Zhou. I'm a research manager from Waymo. Today I'm going to talk about scalable perception for autonomous driving. So Waymo is the self-driving car company under Alphabet. Our goal is to build the most experienced driver in the world. Waymo One is our robot taxi service for moving people, and Waymo Via is our trucking and local delivery service for moving goods. Started in 2009 as a self-driving project inside Google, our journey up to today has covered 20 million miles on public roads, 15 billion miles in simulation, and across 25 cities in the US. Today at Waymo, we are offering the world's first fully autonomous service with 100% of the rides driverless. Here, I want to show you how it feels when sitting in a Waymo vehicle without a driver in front of you.
Hey guys, my ride is here. Here we go. Check this out.
This car is all yours with no one up front.
Oh, wait a minute. We're going red light. No, we're turning right on red. Huh. How about that? Right on red. Boy, he gets with it, doesn't he? He steps on the gas pretty good. Or she. Yeah.
See? No one up there. So crazy.
Yes. Let me tell you why. We've been doing this since 2018 when they had drivers in the front seat that could manually take over just in case. So yes, I'm quite comfortable with this.
Work zone, speed limit 35. Yep, and nailing that 35, no problem.
Thank you.
All right, we're coming to a stop sign. Let's see what they're gonna do. Oh, they're adjusting. Get ready. Hey, whipping it. This car drives better than some of y'all.
So in today's presentation, I'm going to talk about how can we scale up perception in autonomy stack. So if you think about the problem of scalability, we can project it into 5 different dimensions. And among the 5 dimensions, the model generalization, the output quality, and the computational efficiency are critical metrics and attributes for onboard model deployment. There are many research papers published in recent years proposing new network architecture and really pushing the limit along some of these dimensions. To fully scale up perception, applications in the offboard setting have received more attention in recent years. Here, I list 2 representative directions. One is labeling automation, and the other is data flexibility. These 2 applications will provide high-quality data for training onboard perception system. So by coupling the development in onboard and offboard settings, we can potentially accelerate the advancement of the overall perception stack. So in the rest part of the talk, I will first go over some of our work in the onboard setting, and then I will talk about applications in offboard setting. First, on the model generalization, I want to present our recent paper to appear in CCV. The title is SPG, Unsupervised Adaptation for 3D Object Detection via Semantic Point Generation. So in this work, our goal is to generalize a model trained on the dry weather to the raining conditions. The first challenge we're facing is the deteriorated point cloud quality issue. In this image, we can compare pairwisely the range image captured in dry weather to that captured in the raining weather. Here, I use the red color to indicate invalid points. As you can see, compared to the dry weather, the range image captured in the raining days contain many more invalid points that cause very sparse observation by the sensor. Once the point becomes invalid, the intensity channel become also useless. Another finding we found is that the LiDAR scanning pattern in the raining days tends to be more scattered compared to that captured in the dry weather. Occlusion is a common challenge in object detection. To ensure safety, we have to consider the worst case by tackle the occlusion and the raining weather simultaneously. Here is a real example. In the highlighted region on the left of this figure, there's a vehicle which is largely occluded by a wall. However, because it's very close to the planned trajectory of our self-driving car, it is crucial to detect it as soon as possible and understand its intention so as to avoid collision. So if you think about the two problems, deteriorated point cloud quality and the occlusion, the root cause is the missing observation. So our core idea is then, how about we complete the 3D shape of foreground object before we run the detection? Then how can we do that? The first question is, how can we know where the foreground object is? Then we propose to use 3D segmentation. The task here is segmenting foreground 3D voxel from the background, as indicated by the green colored box. Then the second task is, how can we realize the shape recovery? Well, we can also leverage the voxel grid and generate semantic points that should fall inside of a foreground object. As a result, we formulate the SPG as a joint learning task of 3D segmentation and foreground shape recovery. So how can we apply SPG to an existing off-the-shelf 3D detector? The pipeline is rather simple. The pipeline takes original point cloud as input. We first let SPG to consume this original point cloud and generate semantic points. And then we can concatenate semantic point with the original point cloud, and then we can form the augmented point cloud. We then feed the augmented point cloud as the raw point cloud as input to the 3D detector. Okay, I want to note that with SPG, we are only generating about 5% more points compared to the overall number of points in the original point cloud. But we are able to achieve 500% increase, targeted increase in foreground point density. So we have evaluated our method on the Waymo domain adaptation dataset. We choose two base detectors here. One is point pillars, which is popular for its efficiency and easy for implementation in the autonomous driving domain. And the other one is a top-performing detector called a PV-RCNN. All the models in this experiment are trained on the data captured in dry weather and then tested in the raining weather. As listed in these tables, SPG is able to significantly improve both detectors in the raining weather for both vehicle detection and pedestrian detection. Next, we are also interested in applying SPG to the source domain and see if it can enhance 3D detectors in the source domain. So again, we combine SPG with PV-RCN and test it on the Kitty test set. At the time of submission, our method ranked first among all published methods for 3D car detection. In particular, with the help of SPG, our approach demonstrates more pronounced improvement and stronger robustness in detecting hard cases, as highlighted in this table. In the following slides, I'm going to use some visualization to show the high-quality semantic points generated at the full scene level. First, you can see that in this occluded region, SPG is able to generate high-fidelity semantic points to recover the occluded shapes SPG is also able to handle quite well faraway objects. Large vehicles are generally considered challenging in object detection because the large vehicle can be occluded by other agents. With the help of SPG, we are able to recover the full shape of such type of vehicles, and that really makes the detection a lot easier. Now, I want to switch to model quality. This is a paper published in CVPR this year. It's called 3D MEN, 3D Multi-Frame Attention Network for Object Detection. In this work, our goal is to learn to fuse complementary information from multi-frame data by using attention layers. This is a very hot topic in the community. So here's a high-level overview of our design. We designed this model as a second stage to an existing proposal network so as to fit in the onboard application. So given the sequence of input frame, we can apply a lightweight backbone network to extract proposal features. And then we apply attention blocks to refine these proposals into the final detection outcome. Let's take a deeper dive into the model architecture. Our network contains two stages. In the first stage, we apply fast single frame detector to extract proposal feature from each input frame. And then we store the proposal feature for all the frames in a memory bank. In the second stage, we apply cross attention between the current frame and all the history frames. We aim to achieve two goals by applying cross attention here. The first one is multi-view alignment, and the other is multi-view feature aggregation. After the second stage, we get a refined prediction as the final output. We have tested our methods on the Waymo open dataset test set. Here I'm reporting results on the vehicle detection and pedestrian detection. Well, compared to the previously published best result, our method leads to about 7% improvement in 3D AP for object detection and more than 2-point improvement in pedestrian 3D detection average precision. So far, we have talked about how to design the network to either improve the input quality or introduce a second stage network to improve the detector itself. By adding additional network, we are adding extra complexity that will cause extra latency in the pipeline. Then, is there a way we can develop a high performance but low latency model? I'm going to show you this work. Range SparseNet for efficient, accurate LiDAR 3D object detection. This work features targeted feature selection via segmentation and a highly efficient backbone based on SparseCom. The core idea is to leverage sparsity. In the literature, existing work leverage occupancy sparsity to reduce computational cost, where they apply convolution operations on top of the non-empty voxels. In this work, we aim to maximize the saving in memory footprint and in latency. So we introduce a new concept called semantic sparsity. That means we want to only apply convolution operations on the foreground voxels. Then how can we get this semantic sparsity? Let's look at the RSN architecture. So the model takes range images as input. It first computes semantic sparsity by doing foreground segmentation. And as a result, you can see the foreground mask is quite clean. The model then gathers features from the foreground pixels and form a sparse feature representation in the top-down view. With additional layers of sparse feature extraction and box regression, we can get the final detection results. We have evaluated our method extensively on the Waymo open dataset. The first task I want to show here is vehicle detection. The red points represent results by RSN. First, let's compare our method with existing approaches with similar latency, which include LaserNet, point pillars, and pillar multi-view net. We can see that RSN is able to demonstrate significantly higher accuracy. Then let's compare to a more stronger detector, which is PVRCN, the Waymo Open Dataset Challenge winner in last year. We see that RSN yields more favorable accuracy, but it has substantially lower latency. Next, on detecting small-sized objects, RSN also maintains the high accuracy and demonstrates more efficiency gain compared to old method listed here. So our newly introduced concept, semantic sparsity, is general, and it can be applied to train other 3D perception models, such as depth estimation or multi-model fusion. So far, we have covered 3 areas in the onboard setting. Now I want to switch gear and present you our work in the offboard setting. So what are the differences between onboard and offboard? First of all, onboard models are constrained with computational resources, but in the offboard setting, we have abundant computational resources. We can leverage clusters or parallel processing over different chips. And second of all, onboard model has to fit in a very tight latency budget, whereas in the offboard, our model can enjoy rather high latency tolerance. And thirdly, onboard model can only have access to adjacent history, whereas in the offboard, our model can tap into the full log captured by the multimodality sensor. And fourthly, for efficiency purpose, the onboard model are designed with low complexity, but in the offboard, we can actually enjoy the freedom to develop a sophisticated pipeline of a chain of powerful model for single task, as long as the result is good. So along this line, I want to first present our paper in CVPR this year. It's called Offboard 3D Object Detection from Point Cloud Sequences. In this work, we aim to realize a automated pipeline that can generate high quality bounding boxes and tracks. And we want to achieve on-par quality with human labelers. So why we are motivated to do this task? The first challenge is the need to reduce labeling cost. To label a 20-second run segment in 3D, a human labeler can easily spend several hours or even days. As we increase self-driving car capacity, the labeling cost can really go up crazily, drastically. And to this end, we propose 3D auto labeling with human in the loop. With this new labeling paradigm, the machines can automatically take care of most of the labeling tasks, and humans only need to attend a few corner cases or fix a few imperfect auto labels. With this new technology, we can achieve the same goal with less cost, or with the same budget, we can achieve more ambitious scores or explore more parallel directions at the same time. Another challenge we want to address is the need for high quality and large volumes of labels. So traditionally in autonomous driving, the onboard perception system publishes signals for both onboard and offboard use cases. There are a wide range of offboard use cases, such as data mining, perception and behavior model training, planning system evaluation, and simulation. As I just mentioned, bounded by the computational resources and tight latency budget, onboard perception models usually does not have satisfactory accuracy for training behavior model or evaluating them. If we do that, it may include unwanted noise. And given there are so many use cases, the requirement of label is at a large volume. Consider these two use cases. We're really motivated to leverage the advantages in the output setting and develop very powerful machine learning model. So our core idea in this work is to leverage the time travel of points. This gives us two benefits. The first one is that we can see different viewpoints of an object when it demonstrates relative motion compared to the self-driving car. And the second benefit is that we can aggregate the object points across time. This will allow us to obtain a dense observation of the object, and that make the pose and dimension estimation problem a lot easier. We can end up having more accurate and consistent estimation of the object. As an example, we can visualize the top-down view of a minivan by aggregating points from a single frame or from multiple frames. As you can see, with a single frame scan, the observation is quite sparse. However, when we aggregate points from more than 100 frames, we can see even subtle details of this minivan. With such a dense observation, the pose and dimension estimation of this object becomes a lot easier. Now I want to walk through this pipeline with you. So our pipeline takes point cloud sequence as input, and we first run 3D object detection to get detection boxes, their classes, and confidence scores. We then apply multi-object tracking to associate detected bounding box through time. Then we collect object tracks. Roughly speaking, we have two types of objects based on their motion state. Static object, which can essentially be viewed and considered as a densified point cloud by aggregating points through the entire track. And the second type is dynamic object. They are moving through the entire sequence, and we can have a complete trajectory of their motion through time. We then apply divide and conquer strategy to process the static object and dynamic object respectively with dedicated model. And in the end, we have the high quality 3D auto labels as output from the pipeline. We first evaluate our auto labeling system and compare it with existing detectors. Again, we choose point pillar and PBRCN as two comparing methods. So in 3D object detection, IOU threshold controls the quality bar, how well we want to match, we want to evaluate the closeness between prediction and the ground truth. 0.7 is commonly set in industry and in academia. When we look at this 0.7 threshold, we can see that 3D auto labeling is able to achieve relative performance improvement by almost 20% compared to PBRCN and more than 40% compared to point pillar. Then let's increase the quality bar by setting the IOU threshold to 0.8. At this high quality bar, our model is able to enlarge the improvement from 20% to 47% compared to PBRCN, and even enlarge the improvement from 40% to 108% compared to point pillar. So this really justifies the need and effectiveness for developing a customized and strong and powerful offboard model. A natural question people may ask is, how good is auto label versus human label? So we run a human label analysis, and here we run two sets of evaluation. One is based on the 3D bounding box. The other is based on the bird's eye view evaluation, which is a top-down projection of 3D box to a flat plane. Again, we adopted two IOU thresholds, 0.7 and 0.8. First, let's look at the 3D evaluation. At IOU 0.7, our auto label get very close performance compared to human labels. And when we move to a higher standard 0.8 LU, our model slightly lag behind. This is mainly due to the head error prediction. Now let's move to the bird's eye view evaluation. When evaluated at a high standard, IOU equals to 0.8, our model is even able to outperform human labels. In the following couple of slides, I want to show you some applications of auto labels. The first one is at a low label regime. In this task, our goal is to achieve comparable performance by using only 10% of human labels. The detectors and 3D auto labeling pipeline are trained with only 10% of human labels. As you can see, if the model is only trained with 10% human label, the performance is quite low, and it is far from satisfactory compared to the model used full supervision. However, adding auto labels into training, we can actually close the performance gap and achieve a comparable performance compared to fully supervised training. This result really indicates that our auto label is able to achieve 10x label reduction at a low data regime. The second application is unsupervised adaptation. As I've introduced in the SPG paper, here we are also doing similar work. We want to generalize a model trained on the dry weather, but we want to generalize it to the rainy weather. Again, the model can only leverage human labels on the dry weather. So how can we do it? There are 3 steps, which are very simple. First, we can send our vehicle to the rainy weather and collect some raw data. And then we apply our system and generate auto label on these data. Then we combine the data from dry and rainy weather and train the model again. As a result, we can see that the auto labeling pipeline can quickly and significantly boost the model performance in a target domain. Finally, I'm going to touch on data flexibility. This work is called a Surfel GAN, where we propose a scalable solution for generate realistic camera images for novel self-driving car poses and for novel scene configurations. So how do we achieve this? The first step is to leverage a sequence of camera images and the paired LiDAR sequence to reconstruct the 3D world. The results are represented as a Surfel map and a high-quality asset of 3D vehicles. Then, based on the 3D world we just reconstructed, we can render novel view as Surfel image. From the left to the right are the view from the logged data. The middle column is the view when we add a random perturbation. And then the third column on the right is the view from other agents' perspective. As you can see, the rendered Surfel image has a different quality compared to the camera image mounted on the self-driving car. Then we propose to use GAN to enhance the image realism. And the net output is shown in the middle column. As you can see, the GAN is able to do quite a well job in filling the background with high fidelity and give a fine touch to the image details. The first application, as I already introduced, is the novel view synthesis. Here, we can take a logged image and render a novel view at a proximity location. And then the system will give a fine touch and refine the Surfel image into a realistic image. The second application is novel scene configuration synthesis, where the input are original Surfels in the reconstructed 3D world. Now we can specify how do we want to perturb a foreground object? For example, in the top-down row, we can change the location of the vehicle, or in the top-down, in the bottom row, we can adjust the heading of this vehicle. And the network will output a highly realistic image given the new scene configuration. So now I want to conclude my talk. I want to thank you all for listening.
Yeah, thank you very much for that wonderful presentations, and that was a really nice one. I wouldn't know if there's anyone with questions. You may type your questions in the chat or just decide to ask a question maybe by a raise of hand. But in the meantime, I can just engage with you with a few questions, and maybe you could respond while other people prepare their questions. So so I was wondering in terms of generalization, how is the performance of the detection model in the rain weather in comparison with the dry weather? Because maybe I missed it, but I didn't see maybe a comparison between the performance in the raining weather and in the dry weather. And I also noticed that there's a bit increase in latency when it comes to the performance of your method, the detection method, the SDC and the PVRC method, and well, good average precision, but it looks like the timing for the runtime or the latency was kind of high. So what's the trade-off between detection time and average precision, especially in a critical domain like autonomous driving? Yeah, I'm just wondering. And yeah, I'm also thinking if this approach is like, how far are we from employing this kind of approach in detecting maybe actions of road agents and maybe their locations, relative locations to an ego vehicle on the road. Yeah, basically.
Mm-hmm. So I think your question touches three aspects. The first is the detector performance between raining weather and the dry weather. The second is the latency, the extra latency we introduced. And thirdly, how well it can be applied in practice to model the motion. So first of all, on the model gap, on the performance gap between dry and raining weather, we see more than 15% average precision drop when we apply the same model to dry and raining weather. But so that poses this detection in raining weather is a really challenging problem. And that is why we published a data set called the Waymo domain adaptation dataset. And you're right, with this newly introduced network SPG, we are adding some extra latency. But as I guess I can show in the backup slide here, when we apply the SPG with PVRC, we are only adding about 12% of latency, extra latency, and only 3% of extra parameters in terms of the model complexity. So I would say the model, the extra latency we introduced is marginal compared to this top performing detector. Okay. And to your third question, how far are we away from using this technology for real real world deployment of model motions? So I think this is academic research where we have only focused on using LiDAR sensor, but for the highest safety of self-driving car, we're using multi-model sensors where camera and radar system can be leveraged, which can largely close the performance gap that the LiDAR is incapable of. With those signals in play, we are able to do quite a while, even in the raining weather.
Thank you very much. Yeah.
Did I answer your question?
Yes, perfectly, thanks. I don't know if anyone else has any question.
Yeah, because actually I have one, also very related to what you just said. So like you said, like in industry, we are not just using LiDAR and we're using multimodal, that's for sure thing, right? But I didn't really hear so far about any radar research in Waymo. Is there, I mean, is there a lot of team are doing that at Waymo right now? Like what's the status? I mean, if it's not confidential, I mean, if you can share to some extent.
Yeah, I think you have to stay tuned. There might be more updates from the Waymo side, but what I can tell is that in Waymo, we have a deeply coupled hardware team and a software team really inventing the next generation of radar technology to boost our performance in perception.